Well, now we are in section 4, in which we have to match entries of columns 1 and 2. So question 16 says 4 capacitors A, B, C and D are connected to a battery as shown in figure. A dielectric slab is then inserted in capacitor D as shown. Then match the entries of column 1 with those of column 2. So here is a circuit. We have been given, there is a cell and there are 4 capacitors A, B, C and D, and a dielectric slab is inserted in capacitor D as shown. Let's do the working now. Now what happens when the dielectric is inserted? The capacitance of obviously capacitor D will increase, and which means the capacitance of C and D in series will also increase, which means capacitance between these 2 points will also increase. We can mark these 2 points. Let's call this point as small a and this point as small b. So the capacitance of the network to the right of AB, right, will increase, and overall capacitance of the circuit will also increase clearly. Now if that is the case, then overall charge will also increase, which clearly means that charge on A will increase, right? We don't have to do any calculation. We just have to be analytical and logical. As the dielectric is inserted in D, its capacitance increases, and which means total capacitance of the network also increases, which means overall charge will increase. And so for A, charge will increase, and if charge on A is increased, the potential difference across A will also increase. So for capacitor A, charge increases, so P is the correct match, Q is not, and voltage increases, so S is also a correct match. So for A, P and S will match. Let's look at for capacitor B now. Now the potential difference across point A and B will now decrease, because the potential difference across A has increased and the cell will have same constant EMF. So that means potential difference between A and B will decrease because potential difference across A has increased. That being the case, charge on B will decrease and potential difference across B will also decrease. So that means for B we have the correct match as charge decreases, Q, and voltage decreases, R also. Let's look at capacitor C now. What happens to capacitor C? So we see that the total charge has increased, charge on A has increased, and charge on B has decreased, and total charge has also increased, which means definitely charge on C has increased, and which again means that potential difference across C has also increased. So for C, the correct match should be charge increases and voltage also increases. So P and S is the correct match for C. Let us look at D now. For D, if charge on C has increased, charge on D has also increased. Okay. Now remember, potential difference between these 2 points has decreased and potential difference between across capacitor C has increased. So it definitely means that voltage across D has decreased. So that means for D we have charge increases and voltage decreases. So P and R are the correct match for D. So this is our answer to question 16. Let's go to the next question now. Question 17 is also a column matching type question. It says column 1 contains 4 charge configurations and column 2 contains properties. Match the entries of column 1 with those of column 2. And column 1, entry A is a uniformly charged non-conducting sphere with spherical cavity. B has a uniformly charged non-conducting sphere with spherical cavity. In C we have a uniformly charged non-conducting infinitely long rod with a spherical cavity, and D has uniformly charged infinitely long cylinder with a cylindrical cavity all along axis. Entries in column 2 are: electric potential is constant in cavity, electric field is uniform in cavity, non-zero. R says electric potential is not constant in cavity. S says electric field is not uniform in cavity, non-zero. And T says electric field is 0 at O. So let's look at entry A first in column 1. The uniformly charged non-conducting sphere with spherical cavity. Now we know that the electric field is 0 inside this spherical cavity. Potential is constant. So for A, the correct match is P and T. The electric potential is constant in cavity and electric field at point O is 0. Let us look at B now. Now there is a cavity in this, there is a spherical cavity in a uniformly charged non-conducting sphere, but this is not concentric with the sphere itself. The cavity is not concentric with the sphere itself. So we know that in this case electric field is uniform and non-zero, which means the electric potential will not be constant inside the cavity. For B, the correct match would be Q and R. As I said, electric field is non-zero and uniform and potential is not constant. For finding expression for electric field in the cylinder, what we do is, so this is superposition of two electric fields. We first look at electric field due to a uniform cylinder of charge which is infinitely long. So at this point P, you want to find the electric field. Let's say this is R1 and we draw a Gaussian, cylindrical Gaussian surface like this, whose length is L and radius is R1. Making use of symmetry, the electric flux through this Gaussian surface will be equal to E into 2 pi R1 into L, and this is equal to charge enclosed, and charge enclosed is equal to density of charge into volume. Volume is pi R1 square L upon epsilon naught, and which means expression for E would be rho R1 by 2 epsilon naught. In fact, in vector form I can, if I write, it will be like this, where R1 vector is this vector. For a uniformly charged sphere, the electric field inside the sphere is given as rho R vector upon 3 epsilon naught. So in this particular case, E inside would be given as, we have one expression like this, rho R1 by 2 epsilon naught, and we can consider that additionally there is a sphere of charge density minus rho put there. So that will create electric field of minus rho, let's put R vector by 3 epsilon naught. Now if I consider that this is the sphere, then this vector is vector R. So we can resolve this R vector in two parts. This part will be again R1 and this part is, let's say, ZK cap. So this is equal to rho R1 by 2 epsilon naught minus rho by 3 epsilon naught into R1 vector plus some constant vector again. If this is Z K cap, and I have considered this to be the z-axis. So this is the expression for electric field inside the cavity. Obviously the electric field inside the cavity is, in general, it is non-uniform and not zero also. What about electric field at the center of this cavity? Electric field at the center of this cavity, if we see, then contribution for both part will be 0. So electric field at the center of this cavity will be 0, but otherwise the electric field inside the cavity is non-uniform. It is 0 at the center of the cavity, and that means C matches with R, S and T. So C matches with R, S and T. Let's look at D now, and let's write here also C matches with R, S and T. Let's look at D now. What is electric field inside the cavity? So if I again draw a cylinder and a cavity here, the expression that we got earlier can be used. The expression was E inside infinitely long uniformly charged cylinder is equal to rho r divided by 2 epsilon naught. So the field inside the cavity can be found by superposing electric field due to two parts. So E inside the cavity will be rho r vector, or let's call it r1 vector, by 2 epsilon naught. R1 vector is the position vector from the axis to that point, and for the cavity it is minus rho, so it's minus rho, and let's say that vector is R2 vector. Again, R2 vector is the vector drawn from the axis of the cavity to that point by 2 epsilon naught. Now we can see that it is equal to rho by 2 epsilon naught and R1 vector minus R2 vector. This is basically position vector of R1 vector minus R2 vector is a constant vector whose magnitude is equal to the distance between the axis of the cylinder, the solid part, to the axis of the cavity. So that means the electric field inside this cavity is uniform, and so the options will be potential will not be constant, electric field is uniform, and so D matches with Q and R. So that completes question 17.